We're now going to take a look at some, I guess you could say, applications of first order differential equations. And these applications, they don't fall into a really nice, tightly defined category. It's a lot of different problems that you essentially convert it into a first order differential equation, but there is no specific formula. But there are a couple concepts that are very helpful when working with these particular types of problems. The first concept is this. If y of t is a function that represents the amount of a quantity, a certain quantity present at time t, right? Then you might recall, I mean, and this is one of the, fundamental ideas of Calc 1 is that your dy dt, the derivative of this function, represents the rate of change of that amount at a particular time. So this represents the instantaneous. I'll put instantaneous in parentheses. It's often implied, but the instantaneous rate at which the quantity is changing, right? So whatever this quantity is, and again, it could represent anything, right? At which the quantity is, let's get this off, so is changing, right? So what this little concept allows us to do is, if, for instance, there is a statement that's referring to the rate of change of something, it means I can equate that to a derivative, which means I will likely end up, and if this happens to be in an equation, right, then all of a sudden I would have a differential equation because I would have dy dt in my equation. So that's one of the first things. The other thing, and this also comes from Calc 1, but this, whereas this first interpretation of the derivative is more of a physical one, this other one is more geometric. You might say somewhat abstract, but it's just the idea that dy dx, it represents, in fact, so dy dx can be interpreted as the slope of a curve, right? And that curve can be given explicitly, so it could be given in this form, or it could be given implicitly, like in this form, right? So it's the if the question says something about the slope of a curve, then you can again equate that to a derivative, right? So this would be, I'll say this would be a slope of a curve in our xy plane in R2. The other concept that's helpful, a third one, I don't know if I said two or three, there are lots of concepts that are helpful. You can't really enumerate them, but these are ones that stand out for this type of problem. It's the idea of proportionality. So in some problems, in fact, some very important physical problems, you might say that the rate of change of the quantity is proportional to something, right? So I just wanted to remind you of some of the notation and some of the consequences of the concept of proportionality. So if, let's say, A is proportional to B, is proportional to B, we write that A, and we use this little symbol. It looks like an alpha. Technically, I think it probably is alpha or something close to alpha, but we write this symbol to mean is proportional to. So this symbol right here means is proportional to, right? And that's fine, but even though this is a nice symbolic statement, it's not something that we tend to work with. We don't really work with proportionalities, we like to work with equations. So we love to see equal signs and, maybe to a lesser extent inequalities, but we tend not to manipulate proportionalities too much. Not that it can't be done, but we would like to convert this into an equation. Well, if A is proportional to B, what that means is that they differ by some constant multiple. It's another way of saying that A is a constant multiple of B. So we tend to write something like that, right? And K is referred to the constant of proportionality. So where K, and it's a constant, it could be positive or negative. And usually there are other bits of information that would be given that would allow you to determine if it's positive or negative. But what we can say is, I'm just going to say that it's not zero, right? So we don't want it to be zero. So where K not equal to zero is called the constant of proportionality, right? The constant of proportionality. So depending on how things are worded, right? You might be given a statement that's saying that two quantities are proportional to each other, right? Or you might be told that the rate of change of something, again, is proportional to something or equal to something. Depending on the wording, you would either set up a direct equation or set up a proportionality statement, which you can then convert to an equation. If you see the word slope, think about dy dx. So let's just go through and do some of these examples so you can see what exactly I'm referring to. Again, you can't really fit these into any type of neat little box with a nice little formula, but these principles will help. So find an equation of a curve in R2 whose slope at x comma y is given by, and let's say it's simply x plus y, right? And whose curve, right? So it's given by this. Let's say, given that the curve passes through, let's say passes through the point 0, -3, right? So it says find an equation of the curve in R2 whose slope at any point, right, is given by this expression x plus y, given that the curve passes through the point 0, -3. So this is saying if I wanted to know what the slope of the curve is at, let's say 10, 20, the point 10 comma 20, I would just add the x and the y coordinates together, and that would give me the slope, right? But what we want now is the equation of the entire curve, right? Well, this one's fairly easy to translate into a differential equation because it tells us that our slope is x plus y, right? So it tells us that our slope is x plus y, but what is the slope of a curve in R2? It's the derivative, dy dx. So it's telling us that dy dx is equal to x plus y. So there's a differential equation, right? And then what about this information? Well, the fact that the curve, we know that the curve passes through 0, -3, this is our initial condition. So this is telling me that the value of y when x is equal to 0, that value of y is -3. So there we go. So that sentence translates into this initial value problem. And then, since it's asking for the equation of the curve, it means we're going to have to go through some of our analytic methods to actually solve this, right? So we want the actual equation of the curve, right? So we have to think, well, what methods can we use? Well, I look at this and I think, okay, is this separable? I always go to separable first, since that's the simplest of the methods in theory, right? Because the integration can still be difficult, as we've seen. But as far as just a general method, separation of variables is easy. But this one's not separable, right? Because there's no way to factor this product. I'm sorry, we can't factor the sum into a product of a function of x times a function of y. So this one is not separable. So then I ask myself, is it linear? Could I put it in that standard form for a linear equation? And yes, I can. If I subtract y from both sides, then my p of x is -1 and q of x is x. So therefore, it is linear. So we can use our integration factor method. Just as a note, we could use our like general substitution and just make u equals x plus y. That could work, right? But we know that our substitution methods are a little bit more involved. So I'm going to go for the linear approach, right? So let's find our integrating factor. So mu here is e to the integral of -1 dx. So that's e to the -x. Then I'm going to multiply my differential equation by e to the -x. So e to the -x dy dx minus e to the -x times y is equal to x e to the $x. And then I look at the left-hand side, because I always like to see that pattern for the product rule. And there it is. If I say, if my f is e to the -x, then negative e to the -x is my f prime. And then if I say that the y is my g, then dy dx is g prime. So I can see the pattern for my product rule on the left. And then it means what I can do is I can express this left-hand side as the product of the derivative of the product e to the -x times my y. And then on this side, I'll still have my x e to the -x. Then I'm going to integrate both sides. So that means e to the -x times y is the antiderivative of x e to the -x dx. But now I have to use integration by parts. And I look at this and I'm going to opt to use my table method, right? So I choose my u and my dv the same way, differentiate the u column, and I can differentiate it until I get a 0 because we're starting with a polynomial. And then integrate the other column just as many times, and then I'm going to set up my uv there, u times, right? And then technically there's supposed to be the integral of v du, but I can ignore that integral essentially, or I can ignore that because we'll be integrating 0. But don't forget that the signs must alternate, right? So looking at that table, I can write down the antiderivative of x e to the -x. So I have e to the -x times y is equal to, and then this I will have -x e to the -x, and then negative e to the x, e to the -x, and then my plus c, right? Can't forget our constant. Now, remember, our initial condition is that when x is equal to 0, y is equal to -3. So even though I haven't isolated anything yet, this is my implicit general form, I can still just go ahead and solve for C and kind of get it out of the way and not incur any algebraic errors later on. So I'm gonna go ahead and solve for C. So the nice thing is with the initial x value of 0, all the e's become a 1. In addition to that, I have a factor of x here, which is a 0. So all that's really good. And then plus c. So we have a -3 on this side, and then we have a -1 plus c on that side. So this implies that c is equal to -2, right? So remember, the question wants us to find the equation of the curve, right? Now, it doesn't say what kind of equation, right? But I'm going to plug my -2 in for C. So here is an implicit equation of the curve, like this, right? So this is an implicit solution, implicit particular solution if we wanted it. If we wanted the explicit, just it's a simple process, and that's one of the benefits of the linear equations is that you can get the implicit, you can go from the implicit to the explicit simply by dividing by your in this case e to the -x. So y becomes -x minus 1, and then I have -2 over e to the -x, which I will rewrite as -x minus 1 minus 2 e to the positive x. And this is now an explicit equation for our curve. So in this case, the question did not state what form, so that would be appropriate, and that would be appropriate, right? So that's one example. Let's take a look at another example. So let's do number 2. Suppose a quantity changes at a rate that is proportional to the reciprocal. So the reciprocal of the square of the amount present. So square of the amount of the quantity. The amount of the quantity. Let's fix this. Right, so suppose that is true. If at t equals 0, 2 units are present, and at t equals 1, right, so at t equals 1, 4 units are present, determine the amount present as a function of t. All right, so a little bit more for this one, but let's see if we can highlight the keywords. So suppose a quantity changes at a rate that is proportional. All right, so let's do that. So first I'm going to use y just to represent the quantity, right? That's kind of the generic letter. So as I see, the rate is proportional, so the rate of change of any quantity is dy dt. That's proportional to, And then let's see exactly what it's proportional to. It says the reciprocal. So the reciprocal we know is 1 over the square of the amount. Well, the amount is y, right? I am letting the amount be represented by y. That's why this is the rate of change of the amount. And if I now have to write down an expression for the reciprocal of the square of the amount, so this is what I would have, all right? So that, what I just did, the 1 over y squared is the reciprocal of the square of the amount, right? So that gives us our statement of proportionality. Now let's see, what else does it say? If at t equals 0, so y of 0, there are 2 units present. And then at t equals 1, there are 4 units present. So y of 1, we have 4 units. Determine the amount present as a function of t, right? So we have to find y as a function of t. So this is another way of saying, like when we see this as a function of t, it means explicitly. In other words, we don't want y to be a function of itself, right? We don't want it to be explicit. We want it to be, we don't want it to be implicit. We want it to be explicit. Okay, so let's see. Now that we've parsed that paragraph into these statements, the other thing we need to do is to convert this to a differential equation. It's not quite a differential equation yet, but we know if two things are proportional, then they're scalar multiples of each other, right? So we can say that dy dt is equal to some constant, right, times 1 over y squared. And typically we use k as the constant of proportionality. We don't want to use c because c ends up being our constant of integration, right? So you can use, so k is usually plays that role, right? And now we look at this differential equation and say, well, let's see, what category can we put this in? It's definitely separable, so we are going to solve it in that way. I do want to point out, though, that this is Bernoulli, because technically, because you can think of this as k times y to the negative 2, but why would we go through the Bernoulli hassle if we can just separate it, right? So we're going to write this in the separated differential form. So multiply both sides by y squared, multiply both sides by dt. So we have that, and then integrate both sides, right? So we have the antiderivative of y squared dy is equal to the antiderivative of k dt. So on this side we have 1/3 y cubed is equal to kt plus c. So that's where we need our two distinct constants. And now you may have been wondering, why were we given two conditions, right? Well, that's because we have two constants now. We have a constant of proportionality and we have a constant of integration. Again, my preference, and it's that's simply my preference. You might prefer to do it in a slightly different order. As soon as I have any kind of implicit relationship in the form of this equation, I go ahead and solve for all the constants. So let's do that here. So this is telling me that when t is equal to 0, y is equal to 2. So I'm going to plug 2 in here. So I'm going to end up with 8/3 on that side. And then when t is equal to 0, it eliminates this term, right? So we simply have 0 plus c. So our constant of integration is 8/3. And typically usually what happens is if 0 happens to be one of your initial values of the independent variable, when you apply that condition, it usually allows you to solve for the constant of integration. And then the other condition allows you to solve for the constant of proportionality. So y of 1 equals 4, this is telling me that when t is equal to 1, y is equal to 4. Let's plug stuff in and see what we have. So 4 to the third power, that's 64 over 3. Well, times 1/3, that's 64 over 3. So that's the left-hand side. Now, when t is equal to 1, we don't eliminate the k, which is good because we want to solve for k. And then we now know what c is. C is 8/3. So we have plus 8/3. And then subtract 8/3 from both sides. So what do we have there? 64 minus 8. So that is 56 over 3 is equal to k. That's good. So now I can go through and substitute, right? So now I know all my constants, right? My constants have been determined. So I have 1/3. So let me do this. This implies 1/3 y cubed is equal to 56 over 3 times t plus 8 over 3. Multiplying both sides by 3 gives me y cubed is equal to 56t plus 8. And then we can take the cube root of both sides to now express our amount, our quantity, as a function of t. So we have that y is, so you can either write it like this, the cube root of 56t plus 8, or if you wanted to, you could use the fractional exponent 1/3. So 56t plus 8 all to the 1/3 power. Right, and there you have it. So this is our solution, right? So hopefully these two examples are helpful. Like I said, these can be very varied. Any question that has any kind of statement about, you know, a rate of change or a slope, you can always convert it into a differential equation, and then you solve using whatever methods we've discussed. And yep. So I'll see you in the next video when we'll take a look at another very important application. See you then.